Hi everyone. We take a step away from formal methods and proving and go into a serious game to teach not just writing programs, but also comprehending and debugging programs. And so first of all, you might ask yourself the question, why do we do what we do? And here's already a glimpse at how the final product then looks. So first of all, we do this to support, investigate, and motivate to teaching the full programming process in and of itself. So it's not just the creation of programs or learning its syntax or its semantics alone. It's about learning to read programs that are written by others and to comprehend what they're doing. Just earlier in the SPLASH-E track, we also learned about LLMs generating code, and we have to critically think about what the code is then actually doing. And then again, we think it's very important to support this endeavor. All in all, the game that we created, the serious game, is focused on programming novices, and so far we started it to test it out and teach it with novices as young as the age of 12 in German schools, and is designed for an introductory course of roughly 3 hours. You can play with it much longer, but all of the experiments we've done so far were constrained to a 3-hour spectrum where the students usually had no idea of what programming is before, and afterwards hopefully had some idea of what the concept is about. And the game itself, due to the time constraint, focuses mostly on procedural concepts, but there's also object-oriented concepts in the back, but usually we weren't able to get to them in 3 hours. And all of this, as you might have heard so far, is work in progress. So this is one of the non-archival papers, so if you have any ideas about what we're doing and you like the endeavor or something, feel free to come up to me and we can start a discussion, so this would be really nice. So to make a quick jump to what the game looks like and to give you a brief overview, in general we have this playing field here where there's a penguin. We can see it, use a laser pointer, we can see it right here. This is the main character, and then there is a challenge for the students to solve, which of course gets incrementally harder over the levels and teaches them to use various programming concepts. For example, for this level here, they have to write their own program to control the penguin so that it in some way reaches the igloo that is located in the lower right. And the program could look something like this. And there you see a couple of aspects of the language which are already really advanced. So this is of course not the first programs that the students must write, but you can define your own functions. There is an optional typing system. There are loops in various formats. And there are ways that the students can control the penguin in and of itself on the game field to reach and achieve the actual goal. So how did all of this come to pass? So just to give you a quick history of how we arrived at that point. In general, the game was conceived at the university as a way to fill in for a public relations event where we needed something, and so we conceived the idea on March 17th, implemented the game basically in 2 nights, and then, if the animations work, yes, on April 1st we had effectively the first application of this event where we tested it out with a couple of young children in this scenario for the Girls' Day, where in Germany there's an event for girls to try out computer science, electrical engineering, and other studies that are at least stereotypically not as common for girls and women. And then the game went on, and on any other PR event we tested out the game even further. We extended it, we extended the functionality, and over the months and over the years we reached the prototype that we currently have, that we've studied with a couple of children and younger students, and arrived at a feature set that we feel comfortable with to really teach them and show them how the programming concept actually works. So how is the game constructed? What are its features? In general, the whole game runs as a web application. It's also deployed. There will be a QR code in the back where you can test it out if you like. It runs with TypeScript and React, uses Pixie.js to effectively render the scene, and for the language itself, as I mentioned earlier, we're using a custom domain-specific language. We use a combination of the Monaca editor, which is the editor behind Visual Studio Code, and the Langium language framework, which is effectively what came from Eclipse and Xtext, and worked quite well for us to implement the language. And with all of these capabilities, and with our custom DSL, we provided a huge set of features. As I said earlier, it focuses on procedural concepts, but also provides object-oriented principles. It provides things like autocompletion, syntax highlighting, type checking, so on and so forth. It relies on a coroutine implementation of the interpreter, because one of the most important things I haven't told you as far, everything in the game that you see and that you can interact with is actually written in the DSL as well. So we effectively force the students to interact with the language by, if there's water, if there's a fish on the ground, anything that the penguin can interact with in one way or another, the logic, how the student can interact with the penguin, or other penguins that might move over the field as well, is all implemented within the DSL as well. And there's a sophisticated coroutine interpreter that is effectively interleaving all of these semantics and showing the students what's going on. There are many more of these features. We have hints. There's a interrogative time-traveling debugger that they can use to find out what's actually happening. There are various learning paths for basic procedural and even imperative concepts. And there are integrated quizzes because, of course, we wanted to use all of this to find out whether they actually learn something. And so we are effectively recording everything the students do when they're interacting with the environment. And there are extensive docs, even though if you want to check them out, we did this at German schools, so the documentation that's like used as a reference is mostly in German, but we're working on translating that as well. So I already told you that most of the elements that the students can interact with are already written. Well, all of them are also written in the same domain-specific language. What does this mean? For example, here we have a very simple level. It's one of the earlier levels. The penguin, again, has to reach the igloo. Very simple, but now there's another penguin on the game field. And if they actually inspect the implementation of this penguin, that they can see that it will move 3 times into its looking direction, so movement is defined locally. And if we are taking the naive approach of ignoring that penguin and just trying to move 4 steps, we effectively encounter the problem that when we move a step, the other penguin moves a step, it's effectively in the way, and now depending on whether the penguins can push each other, we have a problem that we can no longer reach the igloo. So one of the solutions that now the students have to come up exploratively, and again, if you know programming, that's very easy, you can in any matter delay the movement of the penguin to leave the other penguin to move past and then get through. So what we can, for example, do is we can insert a wait instruction, which then causes the penguin to do nothing for 1 step. And what we now have is that, of course, the penguin can pass because the other penguin moves 1 step forward, and we effectively reach the goal. If I have time, there will be a live demo of this later as well. So with all of these semantics, we of course have other penguins that can be moved, but as I said to you earlier, everything is effectively described in the language. So if we have a bigger field, as I've shown you earlier, you can inspect the water, and again, the water will be implemented within this DSL as well, and again, you can see some more sophisticated features. And on the other hand, for example, the fish that's lying on the ground is implemented as well in that DSL. And then again, if the students want to understand what they can do with these elements, because there will be no direct explanations of what they're actually supposed to do, they have to read through the code and understand what it actually does. And you can see here one of the more specifics of the domain-specific language, because of course there are conditionals, there are loops, there are functions, but one of the 2 important things is that actually every entity can have one special thing that it is able to do that we hide behind an ACT implementation to make it easier for the students to read. Like, for example, other penguins can lay down stones as markers, or can wave hello, or they can trade fishes, or whatever. And on the other hand, we have world references. So with the world keyword, effectively, or with the world object, students can access every element that's on the playing field to effectively interact to check whether the element before them is the other penguin that they were inspecting. And so far, I've only shown you the game in a very simplified state because I only showed you the game board. How does it actually look when you open it up in the browser? It looks roughly like this. So on the left-hand side, you have the code editor where you can write your implementation in the domain-specific language. In the lower left, you have some logging information, which effectively presents you with an information about the current game state. Then on the lower right-hand side, there is some intro hook, again written in German, so that's not important as of now, but it gives a brief primer of what is supposed to be achieved in this level. And in the upper center, slightly left, you have the game controls, which you can then use to run the simulation of your current code. And when the simulation is in play, so yes, when we start the simulation, you will effectively see a stepwise play of how the codes intertwine, and you can see the current state of the actual execution. And you can also stop it, and you can call for the debugger that I was calling to earlier, where you effectively are able to step forward, step backward through the execution and see why the code didn't perform as you might have expected it to. And in the back, we have, of course, these learning paths. So I've shown you some selective levels, but there are actually a couple of levels. So far, we've implemented 42, because, of course, we have implemented 42. And they are separated into these learning paths above. So we start with normal imperative concepts. We then extend them with conditionals, add loops, and in the end, we teach them procedural and functions. And again, we also have object-oriented levels, but we don't get to them in the 3-hour context. Then we have our levels, and each level is effectively indicated either by just whether the student was able to complete the level, or some of these levels also implement score mechanics where they, for example, have to use less instructions, or where there are multiple obvious solutions to the level and they can figure out some more clever ways to solve it actually. And if we're now switching to the quiz implementation, where we're tracking what the students are actually doing, we add these darker teal blue bars, which are effectively quizzes, which can be used to check whether the students have actually understood what they're doing, they're questioned on these things, and they're also recorded depending on what they agreed to, what code they write, when they press the play button, and so on and so forth. So what do these quizzes look like? Again, I've brought some examples here on the slide, and we can do a live demo later. For example, this is one of the earlier quizzes, where we again reiterate on the weighting mechanic. The students are shown a specific playfield state. They are shown the codes of several entities. In this case, again, we just have 2. And then they're questioned. They're, of course, closed answers. There are also quizzes with open answers, what the final game state will be, forcing them to not having any simulation at hand, effectively do the simulation in their head, and again find out what the final game state will be and what the game is supposed to do. And there are, of course, other questions which serve a more general purpose, where we try to grasp their understanding of whether they have really understood what the concept of, for example, looping in this scenario really means, where we ask them, for example, to either come up with predefined or their own scenarios where they would think looping structures and looping instructions could help, either in a programming context or in a general real-world context, to see how their application generalizes. Again, when we are recording these students, we record a lot of information. This is a very simplified and summarized view, where for every level, we record every button press they do. We're kind of like Amazon in that regard, and have a clickstream-like tracking of whatever they intend to achieve. And we track their editor state, which operations they do, when they do these operations. Of course, with the timestamps, we can also intertwine these with students who are brute forcing their solutions by just typing things in, then pressing play, watching whether it works, or students who take a much more systematic approach, where they first think, then they try a solution, and then it takes some time until they press the play button. And also we record the information for the quizzes. And of course, alongside of these things, we also have automated analysis tools to evaluate the results of these things, where we can generate time graphs, so we can see where the student produced which code. We can also identify how they layouted these things, whether they were stumbled by syntactical errors in the language, and whether they use debugging elements, in which scenarios they use the debugging elements, and then we can evaluate these things. So again, I said so far, this is all work in progress. So we so far mainly had things we call preliminary observations, because of course we had children that tried to explore the game, but all of them were in different scenarios. They were children of different age groups. So far we had 56 participants who agreed to data sharing of the ages 12 to 17, but we wouldn't call this a systematic study, because that's what we want to do next with the preliminary results that we have, because again, they were in different scenarios. Some of them already knew programming, and we only used them as a main pre-study guiding way of refining the game's semantics. But again, most of them had little to no prior experience with actual coding, programming, or any of the related terms. So what were our key observations so far? We first of all found that they were all highly motivated. Again, this might be a bias of them knowing that we have a game here that we want to explore, and all of the instructors were pretty motivated, and especially with younger children, that tends to mirror on their emotional state. But what we really found enjoyable and quite surprising is how they engaged in uninitiated, self-started collaborations. So they formed little groups solving harder levels together, or when one of the children was stuck, they helped this child or this other kid or student to solve the specific problem, and even started to explain them how they understood the respective programming concepts. So without us initiating these things, when someone wasn't able to understand what a loop is, someone was happy to help and try to explain them how they understood what the looping structure is actually supposed to do. Furthermore, we found that the debugging was perceived useful, but only after they were shown that debugging can help in a specific individual problem. So far, none of the students started to use the debugger from themselves in these scenarios and try to find out what is wrong. It was always one of the instructors of us walking around, seeing that the student struggles, and then telling them, hey, have you tried the debugger? And then they started using the debugger, and then they actually found the problem rather quickly, and then said they perceived it as useful, and then they started to use it on their own, but it was only after these scenarios where they were confronted with a problem where they actually started using it by themselves. Furthermore, we had active visualization, so I hinted at that earlier, but in the game everything is defined by the current perspective of the penguin. So if you want to turn right, you actually have to turn around the penguin first, which then caused like students on their rotary chairs to try to simulate the game in their mind and rotate with the chair to try to find the current orientation and location of the penguin in a specific state of the program. And after the session, most of them perceived a clear improvement, but then again, we don't want to claim that they actually clearly improved, because that was more of a self-assessment, and we can like infer from how they answered the quizzes, but 3 hours and then a short questionnaire aren't enough to really make definite statements of that so far. So what do we want to achieve with the real big whatever evaluation? One, of course, see the change in motivation. So one thing we want to achieve is that people get motivated with computer science, with programming, but also realizing that it's not just coding and sitting in front of a machine and typing in code, it's also reading code, thinking about simulations, so on and so forth. We've talked about this the whole day. Then we want to analyze their problem-solving approaches. As I said earlier, the preliminary data that we have clearly shows that some of them are really systematic in their way. They try to break down the problem. We can see the code that they write way before they actually even execute the program. And then on the other hand, we have students which like just type in a couple of commands, press play, see that it doesn't work, try to reiterate on the code, and kind of work like an LLM with various iterations on self-improvements until the level is solved. Furthermore, we want to see how like debugging and comprehension ability actually interplay together. Again, we already noticed one of the effects that they don't seem to find an intuitive way of start to using it themselves, but maybe we can find more clearer reasons about how we can incentivize these things. And then again, of course, we want to get more information about the actual learning effect that we can achieve in 3 hours, especially if they've never programmed before. But again, I mean, we have a lot of plans. There are also some open questions. We want to support and compare with other paradigms and interactive tutorial elements, because right now the whole system still relies on some instructors being present, for example, to point them out that, hey, there is a debugger, but we would like it much more if there would be an implemented, like integrated way who realizes, hey, the student is struggling, have you tried the debugger? And then see whether this helps. We also want to involve concurrency because, again, we have all of these entities already interplaying with each other. Currently, there's a deterministic way where effectively they're sequentially interweaved, and so the student can always know when which entity is about to move, and yeah, we want to break that up and make some more concurrent events happening. Of course, we want to compare it with other serious games because there are plenty. And last but not least, we of course want to compare it with the, as it was called this morning, magical text understanding device. So like with how LLMs are able to teach programming and whether there are differences, especially regarding the critical comprehension. And with that, I'm basically at the end. So if you want to check out the game, there's a QR code on the left. It should work on mobile, even though we haven't optimized it to work on mobile. And we can either go directly to the questions, or if you like, I can show you a live demo. I'm open to both. Okay, who's for questions? Who's for the live demo? Okay. Then, by pure means of democratic reasoning, live demo wins. So this, maybe I mirror the displays again, so that I see what you see. All right. So this is the main game. This is where the QR code should have led you to. We can press on start. We can see the level menu. We can start with the first level, because I think that will be very challenging for all of us, where we're effectively introduced by moving the penguin to the igloo on the right. And the only thing the students know so far is that there is this pengu object like that they can write out in the code to do some work. And if they do so, we can also see like the autocompletion at play. So most of the students rather intuitively started to use the autocomplete, maybe they know it from other editors, and then you can effectively re-trigger the autocomplete and then find other methods that you can use with the penguin. And just by pure exploration, you maybe find at one point that there's move. And the only other thing, we told them that they can start the simulation with the play button. So if you now press play, you can see the penguin moving one step, and yeah, that's basically the simulation we've seen so far. And you can go one step back, kind of laggy, and you can again one step forward again, and so you can like debug now this one-step operation, which isn't as helpful. Then, of course, we can take this statement and repeat it a couple of times. And now, luckily, I know how to solve this level. We can make the penguin reach the igloo and proceed to the next level. And there, again, we have the problem that now we can no longer go straight, so they have to re-explore what other options there are and effectively get a grasp on now very, very basic imperative concepts, because they first have to learn how to move the penguin, and then this incrementally gets more and more difficult. Okay? If I now quickly switch to the quiz mode, which we of course don't tell the students how to do, because then they can leave it as well. And now we added the questionnaires, which again are in German. But if we're now playing through games, like we can, for example, retry the level we just tried, and let's speed this up just a little. And we solve it again. And now we think that the students played through all of the 3 hours and had a lot of fun and learned a lot of things and everything went great. And maybe we can even try to look into a questionnaire, which again is in German. But then here are the challenges that they can answer, that they can solve, where they have to answer these questions. We can click on a random button and then say we answered the whole questionnaire, which went great. Then after the quiz ended, we effectively get this beautiful, okay, now with black, this is really unreadable. 1 second. We effectively get this beautiful JSON document, which effectively contains all of the information I've shown you earlier, where we then can see, for example, here, when I press the play button, whether I've resetted the level, what the code looked like when I pressed the play button here. This is the solution that I wrote. And then again, of course, if I now would have taken more approaches and coded more things, there would be much more here to see and then to analyze and evaluate. So yeah, this was a very short live demo. I can also like dip into one of the later levels so that just that you can see what's possible there. Which one do we take? So for example, this is now one of the bigger levels that comes later in the game, where you have many more penguins, where you have to understand what they're doing, where they will move to then again in this level reach the igloo. But then there are many other languages where we have many other levels where you, for example, have to move boxes to allow another penguin to cross path, where there are buttons that then interplay with spikes that then cause a path to become viable or non-viable, where there are ice cubes on the water that actually move non-deterministically, and then you have to effectively like use conditions and everything to wait until the ice block is in front of you, then move one field further, and so on and so on. And this is effectively the level structure that we've prepared, and I think with that we are ready for the questions.
We have 1 minute, 30 seconds.
So it's interesting your observation about the hesitation to use the debugger, because even normal programmers have the same problem. You know, we all reach out to printf. And I have 2 questions. One, were there observations that you were able to make about the students and what might be causing that hesitation in them? The other question is, you said they did eventually use it when it was prompted. Now, was that they had to be prompted on a problem that they were specifically having? Could it have been demoed? Is there a way we could have engineered that? And it sounds like once they prompted it once, they didn't have to be prompted again. Is that correct? Okay.
Yes. I mean, some of them didn't use the debugger even after being prompted, but most of them then did. So it's a difficult question. So in general, we found that most of the students just like prefer the classic software engineering system out print line approach, even though we haven't shown them that you can actually print to the console, so hey. But they could just explore the game state because there was no like permanent failure, so they're like, and we don't want to implement that because that would probably hurt their motivation. But in general, that caused them to just like try out various implementations, and then they were happy. And yes, it was like, if we just showed them the debugger even at the start, because we tried it once at the start with like 20 participants, and I just showed them that you can move back and forward, and that may help you to understand more complicated levels, still no one used them. So it was mostly when they were stuck at the level And the hint was mostly hey, have you tried to use the debugger? You can step forward and you can step backward. And then they started to explore with it, and usually they found it useful, and then they started using it.
When you demoed it at the start did you demo it in such a way that it was like, oh no, I have a problem, therefore this is my solution, rather than just here's the functionality?
Yes, but there was the severe bias that it was a very simple problem, because otherwise I would have needed much more complicated constructs that they then didn't know. So there's still an open challenge how to make the problem complicated enough that they maybe perceive it useful without using loops, functions, and 10 other penguins.
Okay, any generalizable insights that might help us get over debugger hesitation in other developers?
So far, no, but maybe after we did the real study.
Okay.
But we have real hopes in having an automated system that when it perceives users being stuck, then hinting them at, hey, have you tried using the debugger? But we haven't tried that so far, so I can't report on its effectiveness.
I guess we have to continue to the next
Okay,
talk.
okay.
Thank you very much.